Okay, so I'm a postdoc at the University of Cambridge, and I've been working with a few people from the UK and the US on the spatio-temporal characteristics of mixed layer turbulence in an energetic oceanic bond. So we look at the turbulence in a very specific layer of the ocean, which is a mixed layer. So it is a surface buffer layer between the ocean and the atmosphere. And from this modeled vertical section of stratification, we can see that it is a very thin layer that denoted by the thin white line here. So it's a very thin layer of quasi-uniform density and therefore weak stratification. So the mixed layer is forced by the atmosphere, and it hosts an intense turbulence, which ultimately dissipate energy and do intense vertical mixing. So the mixed layer hosts a zoo of motions, including non-wave currents and waves, and these motions realize an intense turbulence. So we can see from this snapshot of relative vorticity at the near surface that at the near surface, there are non-wave currents over a wide range of horizontal scales. So there is a quasi-stationary large-scale circulation, which is denoted by the green contour of time average sea surface height. And this circulation takes place at the scale of oceanic basins. Then we have Eddy's features, with the largest one being the black squares here, which are mesoscale eddies. And they have horizontal scales ranging from hundreds of kilometers to tens of kilometers. And developing between these large-scale features, we have a zoo of submesoscale currents, including submesoscale eddies and submesoscale fronts and filaments. And those features have horizontal scales ranging from tens of kilometers to hundreds of meters. Another type of motion in the mixed layer are internal gravity waves. So we can see from the snapshot of relative vorticity that they correspond to a background signal, which is the most intense at frontal areas. And internal gravity waves, they have a horizontal scale spreading in the meso and submesoscale ranges. So we look at turbulence from an energetic perspective, and this is a scheme of kinetic energy transfers in the ocean for the upper circulation at mean latitude. So at the planetary scale, we have the wind, which forces the upper ocean circulations. Then these currents destabilize and form mesoscale eddies. So this reservoir is key for the global ocean energy budget because it accounts for most of the surface kinetic energy. And in the mesoscale range, the dynamic is mainly balanced, and it's characterized by an inverse turbulent cascade, meaning that kinetic energy is transferred toward larger scales. Kinetic energy can be transferred toward smaller scales when there is a breakdown of geostrophic balance. And this breakdown can take the form of submesoscale eddies, turbulent waves, or fronts, or internal gravity waves. So in this range, in the submesoscale range, the dynamic is partially balanced. And the turbulence in this range can either do a forward cascade, so transferring mesoscale eddies kinetic energy towards smaller scales, eventually down to dissipation scales. And the turbulence can also do an inverse turbulent cascade, straightening mesoscale eddies. So the submesoscale doesn't amount for less energy than the mesoscale one, but it plays a pivotal role in the direction of the energy transfers. So it is key to understand the submesoscale turbulence to understand the ocean dynamic. And in this study, we want to characterize the submesoscale turbulence taking place in the mixed layer. And we want to assess the contribution of the different classes of motion, the submesoscale eddies, fronts, and internal gravity waves. However, the mixed layer turbulence is either partially resolved or needs to be parameterized in models. And adequately representing the mixed layer turbulence, that is important for the fundamental understanding of the mixed layer turbulence, for observational strategies, and for developing physically based parameterization of the energy transfers. So we first characterize the mixed layer turbulence with the contribution of the different classes of motion. And then we want to physically inform the need for high spatio-temporal resolution to infer the mixed layer turbulence. So to do that, we use a realistic numerical simulation of the Drake passage in winter. So we build our numerical simulation on the hydrostatic version of the AMAT-TGCM model. And we use a nesting procedure to increase the numerical resolution. And this work is only based on the finest resolution grid, this one, which solves ocean dynamic down to 1 kilometer, and the output have been saved with a 1 hour time interval. So in this simulation, we have no tides, and we have a 6 hours wind passing. So it means that our internal gravity wave field will be less energetic than compared to observations or other simulations, because we have no internal tide and we have a weak near-inertial wave field. Okay, so the mixed layer hosts a zoo of motions, and to look at the individual contribution of the motions to the turbulence, we need to decompose the motion from one another. So we use a Lagrangian filtering to dissociate non-wave currents from internal waves. In the Lagrangian frame, there is a temporal separation scale between eddies, fronts, and waves, which is the inertial frequency. And that is in contrast with the Eulerian frame, where the characteristic temporal scales of waves is impacted and modified by the Doppler shifting due to the background low frequency circulation. So the Lagrangian filtering, it results in a low pass filtered field, which accounts for the bulk of eddies and fronts, and in a high pass filtered field, which accounts for the bulk of internal gravity waves. And this is a visual example of this decomposition for the near surface kinetic energy. Okay, and then we use another decomposition to be able to interpret the different motions in terms of governing dynamic. So we use a Helmholtz decomposition, which decomposes the horizontal velocity field into a rotational component, which is a good proxy for the geostrophic balance, and into a divergent component, which is a good proxy for the ageostrophic part of motions. So when we combine these two decompositions, we have in total 4 classes of motions at the end. Okay, so we start our analysis by assessing the spatio-temporal scales of the different motions present in the mixed layer. So this is the frequency on y-axis and wave number x-axis spectrum of the kinetic energy of the non-decomposed flow. So if we do this spectral analysis for the 4 classes of motion I just defined, which is this in contours, we see that this kinetic energy continuum in spatio-temporal scales is composed of the 4 classes of motion that overlap in space and time. So we have surface intensified eddies and fronts in the low pass filtered rotational motion in blue. We have the divergent component, mainly the divergent component of fronts in the low pass filtered divergent motions in green. The high-pass filtered motions, they mainly form a continuum at the lower end of the sub-mesoscale range. So it means that the main source of internal gravity wave in our model is the ocean internal dynamic, which results in a weak wave interaction forming the continuum. And that is in contrast with the direct forcing, such as wind, for example. So the high-pass filtered rotational motion, they have a surface intensified vertical structure, and that's consistent with an internal wave continuum and with near-inertial waves. And the high-pass filtered divergent motion So they account for an internal wave continuum, but also for Lie waves. So those waves are generated at the bottom and then propagate to the surface and reach, they reach the surface, as we can see here. So I will skip this for sake of time. We are just like checking we have the right spectral slope, and that's the case. So we are happy. So then we actually infer the turbulent cascade. So to do that, we look at the cross-scale kinetic energy flux. So that is this nonlinear term. And the sign of this term indicates the direction of the flux. So when it is positive, the flux are downscale, so it corresponds to a forward cascade. And when the flux are negative, it corresponds to an upscale energy transfer. And so that's consistent with an inverse turbulent cascade. So when we average in time and space these kinetic energy fluxes, we end up with this curve across the submesoscale range. And we see that the inverse turbulent cascade, so this part, is the most intense, and it covers most of the submesoscale range. And we have a weak forward cascade downscale of about 8 kilometers. So we do this cross-scale kinetic energy flux for the individual and coupled classes of motions. So if we look at interaction between low-pass filtered motion only, so between eddies and fronts, so these interactions, they correspond to the dashed blue line. So these interactions do most of the inverse turbulent cascade and a fraction of the forward cascade. If we look at interaction between high-pass filtered motion, so internal gravity waves, when they interact together, they don't do much for the turbulent cascade. This is a dotted line here, which follows the zero line. And when low-pass filtered motion and high-pass filtered motion interact together, they realize a weak inverse cascade. This is a dashed dotted line, and a fraction of the forward one. So now we have the contribution of the different classes of motion to the mixed layer turbulence, but we don't, and these motions, they contribute to the two turbulent cascades. This is the decomposition of motion into dynamical components, which allows to cleanly separate the inverse cascade from the forward one. So the inverse turbulent cascade is done by interaction between the rotational component of the different motions. And the forward cascade, it is done by the coupling between the rotational and the divergent component of the different classes of motions. So we can note that the rotational component is important for both the inverse and forward cascade. So if we look at the kinetic energy flux for the different dynamical components, we see that they don't change sign across scales, and they only contribute to one turbulent cascade. And when we add together the different dynamical components, so this is the blue line, and the net turbulent cascade, it changes direction when there is a balance between the dynamical components. So it means that the contribution of motion to the turbulent cascade, it is driven by their partitioning between the dynamical component. So if we take, for example, the low-pass filtered motion, so eddies and rotational fronts, they are largely rotational, this across all spatial scales. So they do a large inverse turbulent cascade in orange. And this large inverse turbulent cascade, it largely compensates the forward one. When we look at the coupling between the low-pass and high-pass filtered motion, with the high-pass filtered motion being roughly equipartitioned between rotational and divergent components, so they do an inverse and forward cascade of similar magnitudes, which weakly compensate. So this is why we get a roughly similar inverse and forward turbulent cascade. So to sum up, we see that the different classes of motions, they have different contribution to the turbulence, but we need all of them to get a comprehensive picture of the turbulence, especially for the forward part of the cascade. But noting that, it has implication for the spatial temporal resolution of motion, because Okay, because we have seen that all classes of motion, they spread up to roughly small spatial-temporal scales. So we tested the sensitivity of the winter mixed layer turbulence to the spatial-temporal resolution. And to do that, we coarsen our model. So this is a model benchmark I just presented to you. So if we slightly coarsen our resolution, we filter a bit of all the classes of motion, basically. And this results in a slightly coarser winter mixed layer turbulence. So we have steeper spectral slope. We have a forward cascade, which is quasi-null. And we have an inverse turbulent cascade, which is underestimated by up to 30%. So it shows the importance of high spatial temporal scales for both the inverse and the forward turbulent cascade. So then if we go extreme and we look at a mesoscale only scenario with only the low pass filtered rotational motions, we have spectral slope typical of the quasi-geostrophic turbulence theory. And we have only an inverse turbulent cascade, which is underestimated by about or more than 50%. So it shows the key contribution of the submesoscale range to the inverse turbulent cascade. Okay, so to conclude, we have physically informed the need for high spatial temporal resolution to infer the mixed layer turbulence. So there is a zoo of non-wave current and internal gravity waves in the mixed layer. These motions, they have different governing dynamic, but they overlap in space and time. And the contribution of this motion to the turbulent cascade varies with their partitioning into dynamical components and with their spatial temporal scales. So we have shown that in the Drake passage in winter, when submesoscale eddies interact with the rotational part of front, they mainly do an inverse turbulent cascade. And when submesoscale eddies, front and internal gravity wave, when they interact all together, they weakly do an inverse turbulent cascade and a weak forward one. So our result, they would advocate for the parametrization of this turbulent cascade because it requires high spatial temporal resolution, and that represents a large computational or storage cost, depending on your strategy to infer the turbulent cascade. Thank you.